I'm Jason Schweinsberg, and I'm going to speak about some new joint work with Matt Roberts that involves using branching Brownian motion with an inhomogeneous branching rate to model populations undergoing selection. The preprint can be found on the archive at this address here. Now, in populations undergoing selection, we think of each individual as having a certain fitness level, and individuals can acquire beneficial mutations which increase their fitness. It's natural then to ask how the distribution of the fitness levels of individuals in the population evolves over time. Now, a number of papers in the biology literature have considered this question, and they've generally come to the conclusion that under a wide range of circumstances, the fitness distribution evolves like a Gaussian traveling wave. That is, suppose at some time t1, we record the fitness level of every individual in the population and plot those values in a histogram. Then we should see a Gaussian distribution as pictured here. Then over time, as the population evolves, the fitness of the population increases, so that at some later time t2, the fitness distribution may be over here. And so we see this Gaussian traveling wave with the mean of the Gaussian fitness distribution moving ahead at constant speed. Now, this idea of describing the evolution of the fitness distribution by a traveling wave goes back at least to this work of Simmering, Levine, and Kessler. These more recent papers also derived the Gaussian shape for the fitness distribution. But while several of these papers were very detailed and sophisticated, they were not written in a mathematically rigorous way. Now, there has been some rigorous work in this direction. Durrett and Mayberry considered a population model in which there are always n individuals in the population, and individuals each acquire beneficial mutations at rate mu sub n, and they took mu sub n to be 1 over n to a power between 0 and 1. In 2017, I studied a similar model with slightly faster mutation rates. And in both of these papers, the authors rigorously established traveling wave behavior. However, at a typical time, most individuals in the population end up having exactly the same number of beneficial mutations, so that the fitness distribution of the population really converges to a point mass as n goes to infinity, rather than converging to a Gaussian distribution. So the question that motivated the current work is whether we could formulate a population model involving selection in which we could rigorously establish that the fitness distribution of the population converges to a Gaussian distribution. For the parameter ranges considered in these earlier papers, the mutation rates are sufficiently slow that the process retains a discrete flavor, with individual mutations having a significant impact on the overall evolution of the population. But suppose we consider much faster mutation rates, so that individuals acquire many mutations in a short time, and each mutation has only a small effect on the individual's fitness. Then the fitness of an individual changes over time like a random walk as different mutations appear. And this random walk should be well approximated by Brownian motion as long as the mutations appear frequently enough. And this idea that individual mutations should have only a small effect on fitness is called the infinitesimal model in population genetics. So this leads to the following model based on branching Brownian motion. We begin at time 0 with some configuration of particles on the real line. Each particle represents an individual in a population, and the position of the particle corresponds to the fitness level of the individual. Each particle independently moves according to one-dimensional Brownian motion with a drift of negative rho. We assume that each particle dies at rate 1, and a particle at the location x splits into two particles at the rate 1 plus beta times x, so that particles with higher fitness are more likely to branch. Now, if x is less than -1 over beta, we can't have the birth rate being negative, So we'll set the birth rate to 0 and increase the death rate so that the difference between the birth and death rates is always exactly beta times x. And in fact, as long as the difference between the birth and death rates is beta times x, there's quite a bit of flexibility in the exact choices of the birth and death rates. And I should mention that this model was previously studied by Neher and Halaschek, and most of our results were obtained in their paper using non-rigorous arguments. And so for this model, we were able to show that if rho cubed is much larger than beta, but rho is going to 0, then under certain conditions on the initial configuration of particles, after a sufficiently long time, the empirical distribution of the particle locations will be approximately Gaussian. The initial conditions are needed to ensure that there are many particles at time 0 that are likely to have descendants surviving a long time into the future. And that's necessary because the descendants of any individual particle have a very high probability of simply dying out. Now, perhaps the easiest way to see how the Gaussian distribution arises is to use heuristics based on large deviations methods that came from this earlier work of Beresticki, Brunet, Harris, and Roberts. If we start with one particle at rho squared over 2 beta, which turns out to be approximately where the fittest particles will be located, then we can calculate the most likely trajectory that a particle would follow in order to end up at y after a very large time t. And then we can estimate the number of particles that follow roughly that trajectory. And that gives us an estimate of the number of particles that should be near y at time t, which we calculate should be approximately e to the power g of y, where g of y is given by this expression here. And because g prime of 0 is 0, while the second derivative is minus beta over rho, we see that the distribution of the particle locations after a large time t should be approximately Gaussian with a mean of 0 and a variance of rho over beta. Now, it turns out that the proof of this result goes a different route, mostly using first moment calculations to determine the typical behavior of the process, second moment calculations to control the fluctuations, and truncation arguments to remove the particles that drift unusually far to the right, which otherwise would dominate the moment calculations because they have so many offspring. Finally, I want to mention some topics for future work. In any population model, it's natural to ask how to describe the genealogy of the population. And it seems clear from the analysis that we've done that the genealogy should be described by a process called the Bolthausen-Snettmann coalescent, as had been predicted by Neher and Halaschek. This would be similar to a result in my earlier paper with Julian and Nathaniel Beresticki, where we considered branching Brownian motion with a constant branching rate in which particles are killed at the origin, corresponding to a different way of modeling selection in which particles die when their fitness drops below a threshold. The fitness distributions are known to be quite different for these two models, but we believe that the genealogies are the same. Another topic for future work is to consider discrete population models in which there are always n individuals in the population and individuals acquire mutations one at a time that increase their fitness. We believe that our results should also hold for such models, provided that the mutation rate is sufficiently large and the fitness advantage resulting from an individual mutation is sufficiently small. And because the convergence of random walk to Brownian motion is fairly robust, we expect that the results for branching Brownian motion may carry over to a fairly wide class of population models. For example, the correspondence should hold even if the mutations are deleterious, or if the fitness change resulting from a mutation is random. Establishing these results rigorously for the discrete population models may be quite challenging, however, because one loses a lot of independence when considering a population of a fixed size. Thank you.